Firing a bullet at a wooden block. A small wooden block with mass 0.8 kilograms is suspended from the lower end of a light cord that is 1.6 meters long. The block is initially at rest. A bullet with mass 12 grams is fired at the block with a horizontal velocity v0. The bullet strikes the block and becomes embedded in it. After the collision, the combined object swings on the end of the cord. When the block has risen a vertical height of 0.8 meters, the tension in the cord is 4.8 newtons. What was the initial speed of the bullet? So here is the bullet coming with an initial horizontal velocity v0, hitting the wooden block, gets embedded in it. The combined object moves up to a vertical distance h with respect to the bottom, making an angle theta with the horizontal. So from this geometry, first of all, we have the length of the cord, r is equal to 1.6 meters. The height is h is 0.8 meters. And because the bullet gets embedded in this block, this is going to be a perfectly inelastic collision. We can see from this geometry that if I go up a distance h with respect to the bottom, then this side will be r minus h for this triangle, and I can read the cosine of the angle theta to be r minus h divided by r. So we have cosine theta is equal to r minus h divided by r, which is 0.8 divided by 1.6. So we obtain 1/2. Therefore, this angle is 60 degrees. Cosine 60 is 1/2. Okay. Now, in a perfectly inelastic collision, we have the net external force acting on the system equal to 0. Therefore, the total linear momentum is a conserved quantity. So we have linear momentum conservation. So we can write the total initial linear momentum to be mass of the bullet times the velocity of the bullet. The mass of the bullet was 12 grams. The velocity is unknown, so it's 12 10 to minus 3. The velocity is in I hat direction, v0 I hat, so this is 0.012 v0 I hat direction. The final total linear momentum is mass of the bullet plus mass of the wooden block, the total mass, times the final velocity after the collision. This will be 0.8. Mass of the wooden block is 0.8 kilograms. So it is 0.8 plus 0.012 kilograms times the final velocity, which is 0.812 times the final velocity. So since the linear momentum is conserved, initial total linear momentum before the collision must be equal to the final linear momentum after the collision. So 0.812 v final is equal to 0.012 v0 I hat. Therefore, we find that v final is equal to 0.012 divided by 0.812 v0 I hat. So it's actually symbolically mass of the bullet divided by the total mass, mass of the wooden block plus mass of the bullet times V0 I hat. So that's the final velocity. Now, the total mechanical energy, E mechanical, after the collision will be 1/2 the total mass, mass of the block, a bullet plus mass of the wooden block times the final velocity square, which is mass of the bullet square divided by mass of the bullet plus mass of the wooden block square, V0 square. So we have cancellation of one of the total masses, and we see that initially the potential energy is 0. So this is the mechanical energy of the system right after the collision. So this is right after the collision, we have this mechanical energy. Now at a height h, we will have a potential energy which is mass of the bullet plus mass of the wooden block, the total object times g times h, and we will have a kinetic energy at that point, which is 1/2 total mass, mass of the bullet plus mass of the wooden block, velocity v squared. So we don't have any friction that is mentioned during this process. So basically we can say that mechanical energy is conserved for the swing. So during the swing, delta E mechanical is 0. We don't have no friction. We don't have any friction. So mechanical energy will be conserved. Therefore, kinetic energy at height h plus potential energy at height h will be equal to the initial mechanical energy of the system. So we have 1/2 mass of the block, mass of the bullet plus mass of the wooden block, v square, equal to the initial mechanical energy, mass of the bullet square, V0 square, divided by 2 mass of the bullet plus mass of the wooden block. That is this mechanical energy here. And minus the potential energy, the total mass, mass of the block plus mass of the wooden block, GH. So let's call this equation the star equation. All right. So what I want to concentrate on at this point is the free body diagram of the combined object at a height of 0.8 meters. So at this height, when the chord makes an angle theta with respect to the vertical axis, we have the weight, the total weight, mass of the block, bullet plus the wooden block multiplied by g, and then we have the tension in the chord, tension T, making an angle theta with respect to the vertical axis. And as we can see, this is basically part of a circular motion. So this is drawing a circular arc. So we will see that r hat will be making an angle theta with respect to this axis. So you can see as this object starts swinging, it's performing a part of a circular motion. So we can write the net radial force to be mass of the bullet plus mass of the wooden block g cosine theta, the component on the radial axis, minus tension T is equal to the centripetal force minus mb plus mwb v square divided by r, the length of the cord. So the total mass was 0.812 kilograms, 9.8 meters per second square. Cosine theta is 1/2, minus the tension at this point is given in the problem statement to be 4.8 newtons. So minus 4.8 newtons will be equal to minus the total mass 0.812 v square over r, which is 1.6 meters. So we will obtain from this 0.812 v square is equal to 1.31392, and this v is 1.27 meters per second. So if we combine so if we basically combine this result with the star equation, we can write from the star equation, we can write for v square, we are substituting our new result. So star equation gives us 1/2 total mass 0.812 v square. Now what is v square? To be more exact, it is 1.31392 divided by 0.812. That was v square here. This is equal to 1/2 mass of the block bullet squared 0.012 squared v0 squared divided by the total mass 0.812 minus the total mass gh 0.8 meters. So this gives us 0.65696 plus 6.36608 equals to 1/2 0.012 square divided by 0.812 v0 square. So I've taken this term to the left hand side and evaluated it. And finally, if I multiply this, the left side with 2 times 0.812 and divide it by 0.012 square, I can obtain V0 to be 281 meters per second. That was the initial speed of the bullet. Okay. So in this problem, we have a bullet that has an initial speed v0 in the I-hat direction, moving in the I-hat direction, hitting a wooden block, gets embedded in it. That's a perfectly inelastic collision. In perfectly inelastic collisions, linear momentum is conserved, kinetic energy is not conserved. It's inelastic, so there's energy lost during this process. That's because this bullet is experiencing friction inside the block. Okay, so the total system, block and the bullet, basically move up to a certain height, 0.8 meters, while they will go even higher. But we know the tension in the cord at this height, 0.8 meters. So given this information, what is the initial speed of the bullet? So we write linear momentum conservation. Total initial linear momentum is just due to the bullet, mass of the bullet times velocity of the bullet. Final linear momentum after the collision is basically the total mass times final. This is basically just before the collision, and this is just after the collision. All right, and this equation gives us the final velocity of the combined object just after the collision in terms of V0. And after the collision, we have mechanical energy conserved in the system. So we have an initial velocity of the combined object, and this kinetic energy is turning into potential energy as this combined object rises. So at a height h, we will have the initial mechanical energy of the system, which is purely kinetic because I define potential energy to be zero at the bottom of the path. It will be turned into 1/2 total mass v square, which is the kinetic energy plus the potential energy. The total mass times gh is equal to the initial mechanical energy, which is this term. So if I look at the situation at a certain height, at this angle or theta, which I have found to be 60 degrees from the geometry here, I can write the net radial force to be the component of the total weight on the radial axis minus the tension. This is basically a centripetal force, so this must be equal to minus the total mass v square over r. So that gives us v basically to be 1.27 meters per second from this information, and then we can substitute for v or v square this number into this equation, and we can obtain V0, basically isolate V0, and we get our final answer 281 meters per second.